The encoder and decoder blocks in a transformer model include multiple layers that form the neural network for the model. We don't need to go into details of all these layers, but it's useful to consider one of the types of layers that is used in both blocks, which is the attention layer. Attention layer is a technique used to examine a sequence of text tokens and try to quantify the strength of the relationship between them. In particular, self-attention involves considering how other tokens around one particular token influence the token's meaning. In the encoder block, attention is used to examine each token in context and determine an appropriate encoding for its vector embedding. The vector values are based on the relationship between the token and other tokens with which it frequently appears. This contextualized approach means that the same word might have multiple embeddings depending on the context in which it's used. For example, the bark of a tree means something different to I heard a dog bark. In a decoder block, attention layers are used to predict next token in the sequence. For each token generated, the model has the attention layer that takes it into account the sequence of the tokens up to that point. The model considers which of the tokens are the most influential when considering what next token should be. Remember that the attention layer is working with numeric vector representations of the token, not the actual text. In a decoder, the process starts with a sequence of token embeddings representing the text to be completed. So during training, the goal is to predict a vector for the final token in the sequence based on the preceding tokens. The attention layer assigns a numeric weight for each token in the sequence so far. It uses that value to perform a calculation on the weighted vector that produces an attention score that can be used to calculate a possible vector for the next token. In practice, a technique called multi-head attention uses different elements of embedding to calculate multiple attention scores. A neural network is then used to evaluate all possible tokens to determine the most probable token with which to continue the sequence. The process continues iteratively for each token in the sequence, with the output sequence so far being used regressively as the input of the next iteration, essentially building the output of one token at a time. So in reality, the calculation performed by the attention layer are more complex, but the principles can be simplified. A sequence of a token embeddings is fed into the attention layer. Each token is represented as a vector of a numeric value. Then the goal in a decoder is to predict the next token in the sequence, which also be a vector that aligns to an embedding in the model's vocabulary. Then the attention layer evaluates the sequence so far and assigns weight of each of the tokens to represent their relative influence on the next token. The weight can be used to compute a new vector for the next token with an attention score. Multi-head attention uses different elements in the embeddings to calculate multiple alternative tokens. A fully connected network uses the score in the calculated vectors to predict the most probable token from the entire vocabulary. Then finally, the predicted output is appended to the sequence so far, which is used as the input for the next iteration. Keep in mind, during training, the actual sequence token is known. We just mask the ones that come later in the sequence than the token position currently being considered. As in any neural network, the predicted value of the token vector is compared to the actual value of the next vector in the sequence, and the loss is calculated. The weights are then incrementally adjusted to reduce the loss and improve the model. When used for inferencing, predicting the new sequence of tokens, the trained attention layer applies weight that predict the most probable token in the model's vocabulary that is semantically aligned to the sequence so far. With all that said, the transformer models such as GPT-4, the model behind ChatGPT and Bing, is designed to take it in a text input called prompt and generate a syntactically correct output called completion. In effect, the magic of the model is that It has the ability to string a coherent sentence together. This ability doesn't imply any knowledge or intelligence on the part of the model, just a large vocabulary and ability to generate a meaningful sequence of words. What makes a large language models like ChatGPT 4 so powerful is the sheer volume of data which has been trained, public and licensed data from the internet, and the complexity of the network. This enables the model to generate completions that are based on relationships between words and the vocabulary on which the model was trained, often generating output that is indistinguishable from human responses to the same prompt.